Afternoon, everyone. My name is Lucian Pullen, and I will be your tutor for today. Okay, let me just find the right view. I just want to. Okay, there we go. Like I said, I will be your tutor today, and today we will be doing Faraday's law of induction. Okay, now I assume from your classes that you've already started. Now I'm just waiting for it to connect to the YouTube so I can actually see what you'll be seeing. Okay, there. You are able to see what I'm seeing at the moment. Welcome to another Yeba Physics tutoring session with yours truly. And I see there's no one yet in the Teams session. So today what we'll be doing is Faraday's law, named after, of course, the famed English experimental scientist Michael Faraday. Faraday's law. Okay. Now, what is Faraday's law? Okay, I want to actually see what you'll be seeing on your screens. So, okay, you are seeing exactly what I'm seeing. That's good. So, let me retry that. So, Faraday's law. Like I said, it was named after the English former bookbinder who became Humphrey Davy's successor and also has the Faraday medal named after him. Now, Michael Faraday did experiments in both electricity and magnetism. Okay? And it is said that if he knew a little more mathematics, he would have arrived at Maxwell's equations, because Maxwell based a lot of his own work on the work done by Michael Faraday. Okay, but Faraday, not to take anything away from him, was a truly brilliant experimental scientist for someone without a formal education in science training. Just want to find, okay, here it is. Now, what is Faraday's law? Okay, what is Faraday's law? I have here notes. Okay, now Faraday's law says that an EMF, okay, this is what the Faraday's law says. It says that an EMF is induced when a change within a magnetic field or a change in flux. An EMF is induced if the electric flux changes over time. Okay? This is Faraday's law for one loop. Okay, now for many loops you multiply it by the number of loops. This is Faraday's law. It says that the induced EMF, that is the EMF induced inside, the induced EMF is equal to the negative of the change in flux over time times the number of loops there are. Okay, basically a voltage is created with a changing magnetic field, in plain English. Now, I like this law. I love this law. It is a beautiful law tying two separate branches of physics together. Now, question 1. Let me reiterate. Okay, the question is, an induced EMF is produced in, then they give us a whole selection, 5 different answers. So before we do that, let's just restate Faraday's law in its mathematical form, and I'm going to show you here Faraday's law Faraday's law of electromagnetic induction. Okay. It's going to go in here. Just go on Google and search Faraday's law. There it is, the one I just gave you. Okay. It says that the electromotive force, or the induced EMF, is equal to the negative of n, where n is the number of turns, multiplied by the change in the flux over the change in time. Okay, so the EMF now, that gets more mathematical from Lenz's law, but this is Faraday's law. I'm going to give you it in this formula. It says that the induced EMF, this is the induced EMF, and you have it on your screen there. Just go back. Is equal to, and note, many people forget this, the negative of the number of loops multiplied by the change in the electric flux over the change in time. Now, here's another version of this law. It's exactly the same, but we know, or you should know, that electric flux is nothing but the magnetic field multiplied by the cross-sectional area multiplied by the cos of the angle between these two, the area vector and the magnetic field. Okay. Oh, sorry, there is someone already there. Let me just go to Teams. Hello there. I didn't know that someone had already joined. I'm going to share now. I'm already busy here, but I'll go back. No problem. Okay, I usually just keep it off until someone shows up. Let me just show you, share with you. My screen. There we go. Please tell me, can you see my screen there? It has number 1 on it. Avene. Can you please let me know if you can see my screen? Okay, thank you. Okay, now let me just enlarge it. I'll periodically check to see if you are talking in the chat or if you need anything. Now, let me just restart. This session is on Faraday's law. Okay, now Faraday's law in its mathematical form can be stated as such. It says that the induced EMF, this is the induced EMF, is equal to the negative of the number of loops multiplied by the change in the electric flux over the change in time. Okay? Over the change in time. And I did show an example of, well, not an example. If you were to say do your own research for a minute, you'll see there. If you were to search for Faraday's law of magnetic induction, then you will see this exact same law I just wrote down there. Okay, now going back to what we are doing now. Okay, so Faraday's law says that the induced EMF is equal to the negative of the number of loops multiplied by the change in the magnetic flux over the change in time. Now this law can also be rewritten. Remember, we also know that electric flux is equal to the magnetic field multiplied by the cross-sectional area multiplied by the cosine of the angle between the area vector and the magnetic field vector. Okay, so we can combine these two. If we were to combine these two equations, we would get Faraday's law as follows. It would say that the induced EMF is equal to n, the number of loops, multiplied by the change in the magnetic flux, which is B times A times cosine of the angle between them, over delta T. Now, we know now that to induce an EMF, the following must change, okay? There must be either a change in the time, which is usually kept constant, or there must be a change in either the magnetic field or the area. If the magnetic field or the area or the angle between those two changes, then an EMF would be induced. Okay, so if the magnetic field changes, if the area changes, or if the angle between those two changes, then an EMF is usually induced. Now let's look at question number 1. It asks the following. This question asks the following. By the way, those of you who are listening, if you have any questions, just ask, please. Let me just see if no one has any questions yet. So I have there Kanyiswa, Shandukani, and Avene. Okay, welcome guys. Okay, so we have these we already have established now that Faraday's law only changes when the magnetic field changes, when the area changes, or the angle between these two changes, then an EMF is induced. So let's see. The question is, or the question rather asks, an induced EMF is produced in a closed loop of wire when it remains at rest in a non-uniform static magnetic field. Okay, let's dissect that sentence. A closed loop of wire, okay, when it remains at rest in a non-uniform static magnetic field. Yes, you see, if the wire is closed and it remains at rest, that's fine. But in a non-uniform magnetic field means that the magnetic field itself is constantly changing. Meaning, if you look at what we've written here, it means that B, the magnetic field, is currently changing. It's not uniform, it is changing. Let me use another color. For this, for statement number 1, B is changing. So a magnetic field will be induced. Okay, in a non-uniform magnetic field, the magnetic field itself is changing, so an EMF is induced. Question B, a closed loop of wire when it remains at rest in a uniform static magnetic field. No, that will not induce an EMF because the area stays the same, the magnetic field stays the same, and the angle between them stays the same. So no induced EMF. Number C, a closed loop of wire moving at constant velocity in a non-uniform static magnetic field. Okay, so it moves at constant velocity. So basically, from a mechanics point of view, it is basically standing still. So it is moving at a constant velocity through a non-uniform magnetic fields, meaning the field is changing as it's moving. So again, B is changing. The magnetic field is changing again, so an EMF is induced. So C will also induce an EMF. It can't be all of the above because B is not included, and it can't be none of the above because already found that A and C indeed induces an EMF. So let's check. And yes, an EMF is induced in a loop if the following happens. If the closed loop of wire remains at rest in a non-uniform field, or if a closed loop of wire moves at a constant velocity in a non-uniform field. The key here being, of course, that the magnetic field is non-uniform, which translates to this magnetic field is changing. And we know that if the magnetic field changes, the flux changes. And if the flux changes, an EMF is induced, according to Michael Faraday's law. Okay, question number 2. Let's wipe all of that. Let me go back to the black pen. Okay, so question number 2. The question is, for which of the following is an EMF induced? Okay, we have 4 setups there. For which of those 4 setups is an EMF induced? Okay, so for which of them is an EMF induced? Let's see. Number 1, that bar is moving at constant velocity. Okay, the magnetic field. Let's first go to number A. Okay, I'm going to write here A and then say if an EMF is induced. I will say if an EMF is induced. What is A? A is a conducting rod is pulled on a conducting rails. So this circuit is completed with this conducting rod, which is being slid along these conducting rails. Okay, and they are placed in a uniform magnetic field directed into the page. So the magnetic field is going into the page. Okay, so the magnetic field is uniform. The magnetic field does not change. But what does change? Because you see this here, this is the loop. Let me just draw the situation in A. This is A. Okay, we have the conducting rails here. Okay, going that way. We have a resistor here. We have the other set of conducting rails. And then, of course, we have a rod connecting these two or completing the circuit. Okay, so this here, this area, let me use another color. This area here, ladies and gentlemen, here, this area is your loop. It is not a square, but it is indeed a loop. Okay, the current is flowing around this area where the magnetic field is into the page. So the magnetic field is into the page. Okay, the magnetic field is into the page. Now the magnetic field B is constant. That magnetic field is uniform, it's constant. But as this rod is being slid back and forth, this area here, this area inside is changing all of the time. Meaning, now if the area changes, we know that electric flux is equal to BA cos theta. Now if the area changes, it means the flux is changing. And if the flux is changing, an EMF is induced. So, an EMF, what was the original question? For which of the following is an EMF induced? An EMF is induced for A. For A, EMF induced. There's an EMF induced in A. Now let's look at B. What is B? They say B is a conducting loop, moves through a uniform magnetic field directed into the page. So there we have a conducting loop in the drawing there. It's a conducting loop. This is the loop. and it moves through a uniform magnetic field. Okay, the magnetic field is like that. This is the magnetic field, and this loop is being pulled by some velocity v through a uniform field. Okay, so it's not accelerating or decelerating. Okay, the area stays constant and the magnetic field stays constant, which means that this conducting loop is not inducing an EMF. So no EMF is induced in B because area stays constant and the magnetic field stays constant and the angle between them is constant. So no EMF induced. No EMF induced. C, let's see what happens at C. Drawing number C. We have a conducting loop that rotates about an axis perpendicular to the magnetic field. Okay, so the axis is perpendicular to the magnetic field. Now, anything that rotates, let's say this is if this thing rotates, it means the angle between the magnetic field and the area is constantly changing. The angle between the direction of the cross-sectional area and the magnetic field is constantly changing because this loop is rotating. Now, as it's rotating, its area vector points in different directions because it is obviously rotating. Now, if the area vector is pointing in different directions, it means that since the magnetic field is perpendicular to its loop, to the direction, to the axis, let's say its axis is this way. Let me just try and draw. Its axis is in this direction, and they say the magnetic field is perpendicular to it. So let's say the magnetic field is pointing into the page. Okay, it can be pointing to the left as well or to the right. It's also perpendicular. So let's say it's pointing into the page. Now here we have the loop, and it is constantly rotating. Now as it is rotating, now at this moment, its area vector is pointing upwards towards us. Let's say its area vector is pointing towards us. Let's say its area vector is pointing towards us. That's its area vector. Okay, now as it is, because that area vector, remember, is perpendicular to the area itself at 90 degrees. Now as this loop is rotating, that area vector, the angle between the area vector and the magnetic field is constantly changing. Okay, meaning that an EMF is induced. According to Faraday's law, an EMF is induced in C. EMF induced. Reason: the angle between. Remember, this is Faraday's law. Faraday's law says EMF is equal to negative N delta B. Okay, you guys can see it there. Okay, I'll write it here. The bottom, EMF is equal to negative N. I'm going to erase it again. Delta B A cos theta. This theta here is the angle between the area vector and the magnetic field, and that area is constantly changing in this case. So an EMF will be induced. So an EMF is induced in C. Now state drawing number D. Drawing number D is then EMF induced in there. Okay, so constant magnetic field. A conducting loops moves in a magnetic field produced by an infinite current carrying wire. Okay, so the magnetic field is uniform. The area does not change and the angle between them does not change. So no EMF induced. No EMF induced. So no EMF induced. So only drawing A and drawing C will have an induced EMF. So only A and C will have an induced EMF. So A and C. Let's check. We selected that and it is indeed correct. Okay. Now let's move on to question number 3. Let me just get back to the black pen. Question 3. For question 3, we have the figure below is a graph of the magnetic flux through a certain coil of wire as a function of time. So this figure is a graph of the magnetic flux through a certain coil of wire as a function of time. Just check here, is there any questions yet? Okay, so we have a coil of wire. That is we have a drawing there, figure OQ31.1, that graph represents the magnetic flux through a certain coil of wire as a function of time. So we have magnetic flux on the vertical axis and time on the horizontal axis. While now this flux is constantly measured while the radius of the coil is increased, meaning its area is changing, which means the flux will change. The coil is rotated through 1.5 revolutions, so the coil is also rotated, and the external source of the magnetic field is turned off in that order. Okay, so which of the following is true about the ranking of the EMF induced in the coil at the instance marked A through E? Now let's look at this graph. Okay, now the slope of this graph, let's first find out what is the slope of this graph. The slope of this graph, this magnetic flux over time. Okay, the slope of this graph, if you were to find the slope at any point, you would say it is the change in flux over the change in time. The change in flux over the change in time, that is the slope. Now this change in flux over change in time is an EMF. Okay, so they want to know which of the following is true about the ranking of the EMF. Okay, so the slope is equal to the change in flux over the change in time. Now we know that the change in flux over the change in time is equal to E. Okay, remember this is for one coil, so we don't need to write N here. N is 1. Okay, N is 1. So the slope is equal to the EMF. So the negative of the slope is equal to the EMF. Negative is just a constant, so we can put it in. Or we can do this. The slope of that field is equal to the negative of the EMF. Okay, this is what we are given. The slope, if we calculate the slope, it will be the change in the flux. So the change in y over the change in x. Let me rewrite it. Or rather this way. The slope of any graph is equal to the change in y over the change in x. Now in this case, the change in y is the change in flux. And the change in x is the change in time. Now we know that the change in flux over the change in time for one loop is nothing but the negative of the EMF. Okay, so then they ask, the question actually is, which of the following is true about the ranking of EMF induced in the coil from A to E? Okay, now at number A, let's first find where is the EMF the biggest. Okay, where will the EMF be the biggest? It will be where the slope is the highest but negative. Where the slope is the highest but negative. So let's look at the negative slopes. Okay, so A is a negative slope and E is a negative slope. Okay, now which one of those two slopes is higher, A or E? Okay, so it is E. We can see that E at the point E, the slope is much higher than at the point A. So it will be E first. E is bigger than A. Then so we've gotten all the positive EMFs. Now let's look at the place where the EMF is 0. Where is the EMF 0? The EMF will be 0 where the EMF will be 0. These are all positive EMFs, so they will be bigger than the EMF that is 0. So where will the EMF be 0? It will be 0 where the slope is 0. And the slope is 0 at B. And the slope is 0 at D. Okay. Now, at both of these points, the slope is 0. So they are equal to each other. B is equal to D. And a 0 slope is bigger than a negative slope. Now, where will we find a negative slope? At point C. Okay. Which is the only one left. At point C, we will find a negative slope. And that, ladies and gentlemen, is how you approach this problem. Now let's see if they have a ranking in this order. E, which is bigger than A. So if we start with all those by E. Okay, so we have B, C, and D is all starting with E. Then they're all bigger than A. And then they must all be bigger than B. And B must be big. B must be equal to D, which is equal to 0. And which is bigger than C. So B is the correct answer. B is the correct answer. Okay. We've already established the correct answer. You just need to circle it. Okay. So that is the correct answer. In terms of just pure math. Well, basic math, I should say. Because that is really, really, really basic math. Next question. Question 4. A circuit. So here we have a circuit with a magnetic field going into the page. And this circuit consists of a conducting movable bar, okay, and a light bulb connected to two conducting rails as shown. Okay. Now an external magnetic field is directed perpendicular to the plane of the circuit, so it's going into the page. Which of the following actions will make the bulb light up? Okay. Now the only way this bulb will light up if there is an EMF induced in this wire. And the only way that there will be an EMF induced is when the bar is moved, changing the area, or when the magnetic field strength is changed. So when the bar is moved to the left, it will indeed induce an EMF. When the magnitude of the magnetic field is decreased, so the magnetic field is changed, that will induce an EMF. The magnitude of the magnetic field is increased, that will induce an EMF. The bar is lifted off the rails. Now, when the bar is lifted off the rails, the circuit is dismantled. Okay? It's not complete anymore. And then E, the bar is moved to the right. That will also induce an EMF. So, A, B, C, and E are all correct. They will all induce an EMF, which in turn will light the bulb. Question number 5.
Sorry, sir.
Okay. You can talk.
I'm going to please repeat question 4.
Question 4.
Yes, sir. Can you please repeat it?
Okay. You see here, the question is, it asks, which of the following actions will make this bulb light up? Okay, so we have this bulb connected to two, let's say, copper pipes, okay, or two iron pipes, whatever, but they are conducting, okay, and then we have a bar across these two, okay. So this is it now. In actual fact, if you look at my drawing, so this is what is happening. We have a bar here, it's conducting, okay. Then we have a bar here also conducting. Then we have here a bulb. Okay, we have a bulb there, and then we have a bar across these two. Okay, completing the circuit. This is basically a circuit now completed. Okay, now when we talk about an EMF that is induced, another name for EMF is a voltage. Okay, so basically when you induce an EMF, you're placing a small battery somewhere inside that circuit. Does that make sense? Can you hear me? The lady asked.
Yes, sir.
Okay, so when we induce an EMF, we create a voltage in the circuit which will light up the bulb. Does that make sense?
Yes, sir.
Okay, so everything. So in order for us, now they ask which of the following actions will make the bulb light up. So which will, basically what they're asking, which one of the following actions will induce an EMF? Because an induced EMF will make the bulb light up. So which of the following statements here will make the bulb light up? Now we know from Faraday's law, an EMF is only induced if one of these two things happens. Three things happens. Okay? N you can ignore. It's just one circle, so we can just ignore N. It's a constant. So okay, but let me write it down because children don't like, students don't like it when I ignore stuff. So we have the flux over the changing time. This is Faraday's law. But we know flux, we can rewrite it as follows. Negative N over BA times the cosine of theta over the change in time. And that's the change in that. Okay? This is the flux. This is what flux is. Flux is the magnetic field multiplied by the area multiplied by the cosine of the angle between them. Now, if any of these three things change, or all of them change, then an EMF is induced because it will change the flux, which in turn induces an EMF. Does that make sense?
Yes, sir.
Okay. So, let's see if the bar is moved to the left. If this bar is moved to the left, it's moved this way. It means the area is getting smaller. And if the area is getting smaller, it means the area is changing. So EMF is induced. Okay, so if the EMF is induced, the bulb will light up. Does that make sense?
Yes, sir.
Same reasoning for when the bar is moved to the right. If the bar is moved to the right, the area increases, the area changes, which means the flux changes, which means an EMF is induced. So if the bar is moved while it is still on the rails, important, it must still be on the rails. So if the bar is moved while it's still on the rails, it means the area changes, which means the flux changes, the magnetic flux changes, which means an EMF is induced. Now, if the magnetic field increases or decreases, as in B and C, if the magnetic field changes, if the magnetic flux changes, which means an EMF is induced. So if the area is changed, or if the magnetic field is changed, an EMF will be induced. Does it make sense?
Yes, sir.
Does the question now make sense? The answers?
Yes, sir, they do.
Okay,
They do.
thank you. Let's go on to question number 5. Here we have, they tell us, now if your lecturer is Zola, then, or Dr. Manar, either one of them, they love asking questions from what we do here because they give us these questions to do. Okay, so, question number 5. A flat coil of wire. Okay, so we have a flat coil of wire. It has 20 turns, so N is equal to 20. Each of these turns is an area of 50 cubic centimeters. So 50 square centimeters, sorry. Now 50 square centimeters, okay, is equal to 50 times 10 to the negative 4, isn't it? 50 times 10 to the negative 4 square meters. I will not do the whole dimensional analysis now, so just take my word for it. But it is true, that is 50 times 10 to the negative 4 square meters. Okay, that is the area. Then they say if this flat coil of wire consisting of these number of turns and having that area is positioned perpendicular to a uniform magnetic field, which increases at a constant rate. So the change in the magnetic field increases from its magnitude, from 2 Tesla to 6 Tesla. So it goes final minus initial. So the change in the magnetic field is equal to 4 Tesla. Okay, so the change in the magnetic field is 4 Tesla in 2 seconds. Okay, and the time is 2 seconds. They ask, if the coil has a total resistance of 0.4 ohm, what is the magnitude of the induced current? Okay, so we know that the induced EMF is equal to negative N over the change in BA cosine theta over the change in time. Okay. So induced EMF equal to negative N times BA. So that's the change. Sorry. Write it neater. It's the change in BA cosine theta. Okay, now I'm writing too high. Okay, so it is an induced EMF is the negative of N multiplied by the change in the magnetic flux, which is BA cosine theta over the change in time. So what is the induced EMF? The N we've already established is 20. Okay, so N is 20. We have 20 turns. We have now the change in BA. The area stays constant. Okay, so we can actually take the area out. It's constant. So the area is 50 times 10 to the negative 4. We've established. That's the area times the cosine of the angle between them. They tell us that it's perpendicular. Now the cosine they tell us that the area of is positioned perpendicular to a uniform magnetic field. So if the area is perpendicular to a magnetic field, it means that the area vector is parallel because the area vector is perpendicular as well. If the I don't know how to explain this. It's kind of easy. Let's say this is the area. This is the loop. Okay, let's say this is the loop. Okay, they tell us that the magnetic field B is pointing downwards. Now we know it's perpendicular to it. So we have that the magnetic field is perpendicular to this loop. That's what we've been given. So, but we also know that the area vector is also perpendicular to the loop, meaning the area vector will always be parallel to the magnetic field in this case. And the cosine of 0 is 1. The cosine of 0 is 1 multiplied by the change in the magnetic field, which we've established to be 4.0 Tesla. And the time is, it does this in 2 seconds. Is it 2 seconds? Yes, 2 seconds. Now if you work this out, you get that it's negative 0.2 volts. So this is the EMF that is induced in this loop. Okay, so this loop, this flat coil of wire consisting of 20 turns, this is the EMF that is induced. Okay, now we know that EMF is equal to IR. So Ohm's law. Okay, we have been given EMF is equal, so the induced EMF is equal to the induced current times the resistance. Okay, now we want the induced current. So the induced current I induced is equal to the EMF over the resistance. Now we've established that the EMF is equal to 0.2 volts. So the absolute of the induced EMF is equal to 0.2 volts over the resistance, which they told us is 0.4, and that is just 0.5 amperes. So the current that is currently induced by this changing magnetic field is 0.5 amperes. And if you check click on 0.5 and check, you'll see that it is correct. Let me see. You guys have any questions? Yep.
Can I please ask on the end part? So we are taking the vector of the area.
The angle part. Want me to explain that part?
Yes, sir.
Okay. Let's say this
Yes,
is. Let's draw what is being happen. What is being stated. So let's say this is the area. This is the loop. Okay. I'll just draw it as a square. It has 20 turns, whatever. It doesn't matter. So this is the loop, and they tell us that this loop is perpendicular to a magnetic field. Now, if this is the loop, okay, this would be its area vector. So this is the area vector for this loop. Okay. So this area vector is perpendicular to the loop itself. Okay. An area vector, if you have, let's say, if you look at my drawing here, this is a page. Okay. This is a flat piece of paper. Okay. I'm going to just rotate it. So to the camera, you see now, now this pen that I'm pointing up, this pen would be the area vector for this paper. Okay, this loop of paper. Does that make sense?
Yes, sir.
Okay. Now, this is the exact same thing I've drawn here. So this is a flat loop or coil of wire or whatever you choose to call it. Its area vector is also always perpendicular to it. Okay, so the area vector for a loop of wire is always perpendicular to its cross-sectional area. So here we have the area vector. But then they tell us in this problem that the cross-sectional area. Oh no, this is another question. Let me just go back to that question. Then they tell us here that the area is positioned perpendicular to a uniform magnetic field. If this is the area, remember they don't say the perpendicular to the vector itself. It says the area of this sheet. The area of this sheet is perpendicular to a vector. Now, what else do we know that is perpendicular? The cross-sectional area is perpendicular to the magnetic field. Now, we already know that the area vector is also perpendicular to the magnetic field. This is a fact. The area vector is always perpendicular to the cross-sectional area itself. So the area vector is already perpendicular, but then they go on and they tell us that this area is perpendicular, meaning it is either up or down. Maybe rewrite a different color. Okay, that means that this magnetic field is either up or down. The magnetic field is either up or down. Does that make sense?
Yes, sir.
Because the area, the magnetic field is perpendicular not to this vector. It's not perpendicular to the area vector. It's perpendicular to the area itself. Okay. Now, when two, which means these two, it means then that if you in either situation, whether the magnetic field is up or down, it means this. Remember that cosine theta is the angle between these two vectors, the area vector and the magnetic field vector. But in this case, these two will be parallel. Even if it's pointing upwards, it's still parallel. Okay, does that make sense?
Yes, sir.
Now, when two things are parallel, the angle between them is either 180 or 0 degrees. Okay,
Yes.
I chose, in this case, they don't specify which direction the magnetic field is pointing, so I just chose it to be in the same direction as the area vector, or I chose it to be downwards. You can choose it to be up. If you choose it to be up, all that will change is that the answer at the end will be 0.2 volts instead of negative 0.2 volts. That's the only difference, because the cosine of 180 degrees, which will be the angle in this case between the area vector and the magnetic field, it will be the cosine of 180 degrees, which is negative 1, or the cosine
Yes.
of 0, which is 1. Does that make sense now?
Yes, sir.
Okay.
If the case now is saying that we are given that the it is positioned parallel, like is there a case that it can state in a question that it is parallel, then are you going to change it to be perpendicular? If they say our area is parallel.
Yes. If we were to flip this area, let's say this happens. Let's say the magnetic field stays the same. Let's choose it to be down. Let's say the magnetic field is in this way, that is B, and they say now that this area is parallel, which means the area will now look like this. It is going to be look like this. It is parallel to this magnetic field, which means the area vector for this thing will now point in this direction, because the area vector, remember, will always be perpendicular to the area. Does that make sense? Can you see my drawing?
Yes, sir.
So now
Yes.
the cosine will be cosine of the angle between the two. The angle between these two will then be 90 degrees. And the
Okay, sir.
cosine of 19 is 0.
Yes. Okay, sir. Thank you.
Okay. Basically, if you look at it this way, if this thing, if the both of those, if both of these things is parallel, this magnetic field will never enter into that area. Does it make sense? It'll miss it. It'll just go past it like this. It'll go past it
Yes.
down. So, and Faraday's law, in its simplest form, it just says, remember flux. All flux wants to know, we remember we're dealing with a change in flux, right?
Yes,
All
sir.
flux wants to know is how much of the magnetic field is going through the area. If the area and the magnetic field is parallel to each other, none of the magnetic field will go through the area. Does that make sense? So there will never be an EMF induced.
Okay, sir.
Okay. You good now? Are you good now?
Oh, yes, sir.
Okay, cool. Okay, let's see. Question number 6. I also struggled with this stuff, so I could never get the picturing stuff right, because I always mixed up the area vector and the vector of the area itself. And it's always confusing. And when you start doing, well, you guys are doing Faraday's law now, so you'll be doing Ampere's law soon, I expect. And then writing that exam at the end with all of these formulas and all of this thing to remember. You just need to keep your head. Okay. Now, the coil, the question 6 says, the coil shown in the figure. Now I'm writing in red. So that coil shown in that figure there has 2 turns. Okay, so there's 2 turns. A cross-sectional area of 0.2 meters and a field, a magnetic field that is parallel to the axis of the coil. Now, this is where they always trick you. Note, they state here that the field is parallel to the axis of the coil, meaning that this field, if this is the coil, let's say this is the coil, those 2 coils, this would be the axis of those coil. Now, if the field is parallel to that coil, it means the field is perpendicular to the coil itself, but it is also parallel to the area vector. The field is parallel to the area vector. Now, here's the magnetic field. They give us that B is equal to 4 4,0 4,0 plus 3,0 t squared Tesla. This magnetic field is changing, which means immediately an EMF will be induced because this magnetic field changes with time. As time changes, the magnetic field will change. That T looks ugly. That's how the magnetic field changes. Theta, we've established now, is the angle between the area vector, which is in this case pointing parallel, and the magnetic field is in the same direction. So the angle between them is 0 degrees. And what else do we need? N is equal to 2. And we need what else? That's all that we've been given. Now we know an EMF is induced if the negative of N multiplied by the change in A times B times cosine theta. Now, from math, you know you can just take constants out over the change in T. Now, how else can we write the change in something? Okay, we can write them as a differential. But first, let's take out the constants, okay? What is constant? If the magnetic field is changing, the area stays the same. So we can take out the area. The cosine of theta is going to be the cosine of 0, which is 1. So we can take that out. The cosine of 0 degrees, we can take that out as well. And then we're left with the change in magnetic field over the change in time. Okay? So the induced EMF, ugly. The induced EMF is equal to the negative of N times A times the cosine of 0 is 1. I'm not going to write it again. Over the change in the magnetic field over the change in time. Now the change in something or the delta something can also be written in as a differential. Okay, so dB dt. Now the more perceptive of you will know immediately that this is the differentiation. Okay, this is differentiation. It is the time derivative of the magnetic field. So dB dt, where B is the magnetic field. Okay, so if we were to rewrite it, it would be the negative of N times A d dt of, what is the magnetic field? It changes as 4,0 plus 3,0 t squared. That's how the magnetic field changes. dB dt. Okay. Now what is N? It's 2. We've been given it's 2. What is A? The area has been given as 0.2. Now d dt, so the derivative with respect to t of this whole function is equal to 4. The derivative of 4 is 0. The derivative of 3t squared is 6t. So this here, ladies and gentlemen, if we were to sum it up, is negative 2 times 0.2 is 0.4. 0.4 times 0.6. Let me just check on the calculator here. Oh, I have done it, I think. 0.4 times 0.6. Let me just write it here. 0.4 multiplied by 6t, and they asking us after at 3 seconds. Okay, so 3, where t is, we just plug in 3. And if we continue with this on that way, the answer would be negative 7.2 volts. That is the induced EMF in this here, circuit. So this is the EMF which is induced. Okay. Now if you think about this, just think about it. We haven't done anything. We have not connected a battery, anything to this wire. All we've done is we have somehow pointed a magnetic field through this coil of wire. Okay, and we have then changed the strength of this magnetic field. Okay, we've changed the strength of the magnetic field, and that created or induced an EMF inside this wire. So almost we can call it magic like. It's not actual magic, it's physics. So spontaneously a voltage is created inside of this wire. So if you were to connect a bulb here, anywhere in this wire, that bulb would just suddenly start shining. But all we've done is to create a magnetic field, which is invisible, by the way. So we cannot see what is happening, but all of a sudden the bulb would be shining. But let's check, negative 7.2, and that is correct. Let's go to our last question for today. Okay, this is a long straight conductor. Okay, so we have a long straight conductor lies in a horizontal surface with two coils of wire on either side as shown. Okay, so here we have two wires. So we have a conductor, long straight conductor. The current in the conductor flows northward, so this is the direction of the current flowing. It flows upwards and decreases in magnitude with time. Okay. So if we were to look at it from the top, okay, using your right hand rule, you can actually determine the direction of, these are two wire coils, by the way. So first of all, what you need to establish is the magnetic field induced by this long straight conductor. Okay, if you were to use your right hand rule, point your thumb upwards, your right hand thumb upwards, and then the direction of your curled fingers will be the direction of the magnetic field. So in this case, the magnetic field will go in this circle and it will come out of this coil. Okay, it will come out of that coil. Okay, so that is your right hand rule for the conductor. Very important, it's the right hand rule for the conductor. Now these two are also conductors, these circular conductors. Okay, so we have the magnetic field coming outwards. So if you were to, now you do the exact same thing, but now your fingers, your thumb is now pointing in the direction of the magnetic field, and your curled fingers now will point in the direction in which current will flow. Okay, so if I were to say start on the right hand side, I point my thumb upwards, I see that my curled fingers are going counterclockwise. So, oh no, this is in, sorry, I pointed my fingers in the wrong direction. So I'm pointing my right hand in to the page, which means my curled fingers are pointing clockwise. Okay, so the current induced here is clockwise. So a clockwise current is induced in the right hand loop. Let's go to the left hand loop. If I point my thumb outwards, my curled fingers will point in the anti-clockwise direction. Okay, so that is the direction. So the one on the west will be anti-clockwise, while the one on the right will be clockwise. By this time, the right hand rule should be second nature to you. So clockwise, counterclockwise, no. So counterclockwise in the east coil, no. Clockwise in the east coil, and counterclockwise in the west coil. Let's check. And yes, that is correct. Ladies and gentlemen, those of you who are still listening, thank you for watching. I'm not going to keep you much longer. I'm going to stop sharing now, and if you want to learn more, Arnold will be up next tomorrow, and it's going to be some more problems on Faraday's law. So if you wish to continue with Faraday's law problems, which I would advise because it does help in the end, please do so. Best of luck and enjoy the rest of your day.